In the previous videos, we gave you an introduction to quantum mechanics and looked at some of the popular ways of interpreting how it works in the real world. In this final video, we're going to look at some of the newer and weirder interpretations, ones which don't have such a mainstream following, but nevertheless suggest some intriguing possibilities about the nature of our reality. The first interpretation we're going to look at really just started off as a modification of the Copenhagen interpretation. It's called the Consistent Histories interpretation, and it was proposed by Roger Griffiths in 1984. It follows the basic principles and rules laid out by the Copenhagen interpretation with a few modifications. In this interpretation, classical physics is really just treated as an approximation to quantum phenomena, and quantum probabilities don't refer to the results of measurements, but rather physical states inside a system. The most important idea that Griffiths put forward is that multiple possible realities are incompatible. To illustrate this, let's use an analogy that Griffiths himself used. Here's a picture of a mountain. Now let me draw it from another angle, and another. They all look pretty different, right? But what I'm really doing is drawing a picture of the same mountain from different sides. The pictures could easily be put together to form a single, coherent, completely consistent picture of the mountain. In quantum physics, however, while you can choose which properties to measure, for example, position or momentum, you can't combine the two measurements to give you an accurate idea of what the particle state was before measurement, because there is no simultaneously real position and momentum before you made the measurement. In other words, if we were following quantum rules, you wouldn't be able to stitch together the pictures of the mountain because they weren't all simultaneously real. Now you might be saying, can't the wave function describe a state with multiple possible realities? Well, yes, but what the Consistent Histories interpretation says is that the wave function is just a mathematical tool for computing probabilities of events. But in reality, there will always be a consistent sequence of events, a consistent history, which is how the interpretation got its name. One of the major advantages of the Consistent Histories interpretation over the standard Copenhagen interpretation is that it resolves many of the paradoxes associated with quantum mechanics. For example, the famous Schrödinger's cat paradox can now be resolved, since according to the Consistent Histories interpretation, there cannot be a physical state in which the cat is both dead and alive, since the properties that state that the cat is dead and the ones that state that the cat is alive cannot be true at the same time. The major objection raised to the Consistent Histories interpretation is that it abandons the idea of unicity. That is, the idea that at any given time there is only a single state of the universe which is true, and furthermore that every true statement about the universe must be consistent with this. In the Consistent Histories interpretation, an observer is free to employ different descriptions of the quantum world. In our earlier analogy, the different pictures of the mountain, as long as the pictures are not combined. This seems deeply counterintuitive, but the way that proponents of this theory explain it is by making a comparison with the way the heliocentric model of the solar system replaced the geocentric model. The geocentric model persisted for so long because from everyday observations it seemed that the sun rotated around the Earth. In the same way, the idea of unicity seems self-evident because the everyday macroscopic world can be understood using a single description. Only in the quantum world does unicity break down, which is why we don't notice it. Does this idea really stack up? The second interpretation is called quantum Bayesianism. The basic idea here is that the wave function is nothing but a measurement of an individual's knowledge of the state of a quantum system. In this sense, the wave function is personal, i.e. different for each person. But before we dive into this idea, I should explain the name of the interpretation. The reason it's called Bayesianism is because the idea is derived from a formula called Bayes' formula, which basically tells you the probability of something occurring given that you have prior knowledge of the conditions related to that event. The answer you obtain is dependent on how well you know these conditions, and it's exactly the same principle here. The major principles of quantum Bayesianism are that, number one, all probabilities in a quantum system, including those equal to 0 or 1, are valuations that an observer ascribes to his or her degrees of belief in possible outcomes. As they define and update probabilities, quantum states and measurements are also the personal judgments of the observer. Number two, quantum measurement outcomes are personal experiences for the observer, and while different observers may confer and agree upon the consequences of a measurement, the outcome is always an individual experience. Number three, a measurement apparatus is conceptually an extension of the observer. A good analogy here would be a prosthetic limb, which is both a tool and a part of the individual. The major objection that has been raised regarding quantum Bayesianism is that making quantum theory a matter of personal opinion essentially eliminates the idea that there is any objective reality. In other words, reality exists only in your mind, and someone else's reality may be different from yours. This is an offshoot of a philosophical idea known as solipsism, which basically says that you cannot be sure anything other than your own mind exists. Another problem is while the interpretation makes the observer all-powerful, it fails to give a precise definition of what an observer is. Does the observer have to be human, or even sentient? Could a cat construct a different version of reality to you? This is actually a problem in many quantum mechanical interpretations, but is especially relevant in quantum Bayesianism since the observer is given so much importance. So are these objections enough to disregard the interpretation? The final interpretation is called the cosmological interpretation, and it is very new. It was proposed in an online paper published in 2010 by Anthony Aguirre and Max Tegmark, and it interrelates two seemingly different areas of physics, cosmology and quantum physics. To start off with, Aguirre and Tegmark have made a major assumption about our universe. They've assumed that it's infinite. Now you may be thinking, wait a minute, how can this be consistent with the idea of a Big Bang? If the universe started at some finite time, 13.7 billion years ago, then how can it be infinite today? The answer lies in the eternal inflation theory of the universe, which is an offshoot of the Big Bang theory proposed in 1986. It proposes that the inflationary period lasts forever in most of the universe, and this would produce a hypothetically infinite universe or multiverse. This is the assumption we have to accept if we want to talk about the cosmological interpretation. So now let's get to the interpretation itself, which is really an offshoot of the many worlds interpretation explained in an earlier video. Aguirre and Tegmark stated that assuming an infinite universe, the many worlds interpretation is trivially true, since in an infinite universe, every single possibility of existence would be played out. For example, there would be a corner of the universe where it would be you narrating this video, not me. Similarly, every single quantum mechanical outcome would be played out somewhere in the multiverse, basically the same idea we saw in the many worlds interpretation. Where the cosmological interpretation goes further, it's the idea that these outcomes would occur in the multiverse in precisely the proportions given by quantum mechanical probabilities. In this view, the wave function describes the spatial location of identical quantum systems, and quantum uncertainty is attributable to the observer's inability to identify their location in this collection. So what are the drawbacks of the cosmological interpretation? Well, as stated before, it does rely on the assumption that the universe is infinite, which isn't a widely accepted theory currently. American physicist Paul Steinhardt pointed out that the major flaw in this theory of an infinite universe or multiverse is that it's not falsifiable, which means it can never be proved false and is thus an invalid scientific theory. The reason for this is if we adopt the theory of a multiverse with an infinite set of possibilities, there can never be any measurement or series of measurements which falsifies the theory, since it's so flexible. If the theory of an infinite universe or multiverse cannot be falsified, is this enough to put the cosmological interpretation in doubt? So I hope you enjoyed listening to our series of videos about the interpretation of quantum mechanics. Of course, there are many more interpretations which we haven't covered, and more still that will no doubt be proposed in the future. Will there ever be a consensus? Your guess is as good as mine. Make sure to like and subscribe if you enjoyed the video. From the whole team, thanks for watching.